Hello, everybody. I'd like to thank ShapeBlue and 42On for having me here today. My name is Peter Pouliot from the Ampere Computing, and I'm here to talk to you today about cloud native computing, how cloud native computing is the future of sustainable private cloud. So I'm going to talk a little bit about myself and my history working in private cloud technologies, a little bit about why I'm at Ampere and who Ampere is. And then we'll talk about a little bit about the current state of the industry of clouds, data centers, and infrastructure, and follow that on the next, so kind of the next frontier of computing in that space, and finish off by getting a little bit deeper into cloud native processors. So my name is Peter Pouliot. As I said, I live in Stoneham, Massachusetts. I've been working in open source for roughly about 28 years. Started out working on the GNOME project, worked for SUSE for 9 years, was part of the team that put Linux on Hyper-V, worked on OpenStack for Microsoft for 5.5 years in the early days of private cloud when the Linux distributions were doing things like Eucalyptus. And then continued to do work on OpenStack, other private cloud technologies. Ceph, for example, I've been involved with since back when they were DreamHost. So, at Ampere, I've done a lot to help enable open source ecosystems, specifically if you think of the space, moving to an ARM-based processor, right? There's a leap of faith that needs to occur. So a lot of what I've been able to do in my almost 5 years here at Ampere is work it within the different open source ecosystems and projects specifically, those that are doing maybe native or building ARM binaries. I like to go in and ensure that those binaries are compiled, built, tested on Ampere platforms, right? Because as you guys know, I would imagine there's a lot of folks in here that utilize Raspberry Pis or some of the Tinker boards that are available. We're talking about high performance, high scalable compute for doing real compute intensive workloads, but with ARM server chips in them. So they're actually built like a server chip and not like a Tinkerboard chip. So it's a big difference. So at my time at Microsoft, as I mentioned, I spent helping maintain the Hyper-V infrastructure, which oddly enough, the original Hyper-V driver was actually created by Cloud.com back in early 2000 or late 2010. I was the first person to deploy that and have actually worked in the early days of CloudStack's integration with Hyper-V. That work was actually ported from the work of my team back in probably 2013. I've also spent a lot of time, as I mentioned, working in Ceph. In the early days, it was to try to convince folks to build a Ceph driver for Windows, which recently was developed by some friends of mine who I had worked with at that time back in the early 2010s to help try to do, but it took about 10 years, but they were finally able to get it released. And as of today, in 2019, I actually donated 15 servers to the Ceph Foundation and worked with Sage to get those implemented. So today, all current builds for ARM64 and binaries coming out of the Ceph Foundation are actually done on original Ampere infrastructure. So that's a little bit about me. Here's just some, photos of my journey here, seeing where Ampere's come from the get-go. And for those who don't know much about Ampere, Ampere is the first cloud-native computing company in the industry, right? So we develop chips that are specifically designed for cloud workloads, right? If we and we'll get into a little more, I guess, that, but just looking at this picture, these pictures here, there's some of the state of the evolution, right? Like this is one of the first desktop units that we ever shipped back in 2019. It's still sitting under my desk today. It's the size of a refrigerator. It was a server board that was jammed into a chassis, and we're moving. If you go to this right here is a ASRock rack motherboard that we just released that you guys can go buy on Newegg, where you can build your own ARM server in your house, right? So we've seen the industry, evolve and change a lot over the last five years or so. And just one more interesting anecdote, this rack right here is from Oregon State University Open Source Labs, where I gave them in 2019 a slew of servers, which they built an OpenStack cluster that's publicly available for open source projects who need access to free ARM server compute, can come and request access to that infrastructure for their project. Now, it just so happens at the time at which I gave him that infrastructure, and you have to realize that ARM servers use significantly less power. And my friend Lance at the OSU OSL, he also runs the open power infrastructure for PowerPC, right, for the open source ecosystem. And it's very interesting when you go look at the PDUs of those racks and see the dramatic difference between what it's like to run a rack of ARM servers versus PowerPC or Intel. And specifically in this case, when he actually deployed those servers, he had to go get someone to come and check because the rack of servers at idle use less electricity than the top of rack switches, right? So he needed someone to come and pinch him to come make sure that what he was witnessing was really going on. So, I guess what this should tell you is that the momentum behind changing compute architecture is real, and Ampere is hopefully at the forefront of helping bring ARM-based server computing into private cloud. So, if we look at the history of all this and look at how we got here, right? We went from monolithic computing with mainframes to the client server model, which is truly where a lot of the first virtualization technology came out of, right? To what we call the modern cloud, which even today has evolved from API-driven infrastructure to microservices to containers and an amalgamation of all that, right? So it's it's constantly evolving. The way we deploy is evolving, and what we're seeing is changes in architecture as we evolve. Right? Hold on, too fast. Okay, so if we look at just the landscape of energy data centers, and here in Europe is I was fortunate enough to get to attend CloudFest the last 2 years in a row, and that was first where I learned about the I guess how active the private cloud space is here in Europe. And coming out of primarily OpenStack, where we were told that OpenStack is dead for the last 5 years. The reality of it in here, private cloud technologies are huge. Greenfield, new private cloud technologies are ongoing and increasing. A lot of that we find is driven by the data sovereignty aspects, as well as wanting to control your own infrastructure, right? On top of that, the power consumption is one of those critical I would say aspects that when talking to folks talking about private cloud, that they're concerned about, right? So I think that you'll see, specifically even with the current socioeconomic, political things going on in the area that caused energy prices to skyrocket, changing the momentum about how we compute and the our understanding and ideas of the energy associated with that is necessary. And as we can see, continuing moving forward, this creates a physics problem, right? Like as the amount of energy needed to compute increases, we lose real estate, right? So I live in the Metro Boston area, where our telecommunications infrastructure is over 100 years old. Okay, those buildings are never going to go away. They're not going to change. In some cases, we can't get any more physical power into that building because the physics will not allow it. You can only pull so much copper through the walls of a brick building that's 200 years old, right? So the reality of it is we have to figure out new ways of efficiency to be able to continue to utilize the space that we have, right? And do it in a more efficient and optimized way. So, and obviously, like we said, the time for this is now, right? Like the energy crisis is only going to continue. The compute needs are only going to require more electricity. I think 70% of Ireland's power today goes to powering hyperscalers' data centers, right? There's now policies and moratoriums on building new data center space. So obviously the way we build our infrastructure needs to change to be able to fit within the changing demands of the industry. So I came out of the software side of things. So working at a chip company, you tend to learn a lot of interesting metrics of how things are expressed. So PUE is one of those that just talks about the effectiveness of the data center itself and how it utilizes the energy, right? Typically, we determine it by dividing the total amount of power entering a data center by the power used, when you run your IT equipment, and something in the lower one dot, space is usually pretty good. I know Facebook's years back when they were talking about open compute, I think they were able to achieve something close to 1.1, 1.2 with that PUE in that space. But obviously, putting focus on understanding your power consumption and, I guess managing it properly is going to be key, and understanding the metrics necessary to do that. Important. Now, as I said, I worked on OpenStack for, I guess I still every now and then have to work on OpenStack, but I ran the largest continuous integration in all of OpenStack from 2013 till 2017. We had over 700 servers, 40 racks a year. This is some of it, right? So this you wouldn't see in a normal data center today because you can't put that many servers. In fact, we tripped the circuit. We blew a circuit during the middle of the winter because we're a little bit rebellious and we're stealing power from other people and weren't necessarily paying attention to the circuits we were plugging into. So if those of you who remember 2015, we're in Boston, we had 15 feet of snow. I took the power out of that data center during one of those snowstorms because we plugged too many things into the wrong circuit. So, those are the things that you kind of have to worry about. And once again, when we talk about the physics of the room, the components of those servers like GPUs increase their power consumption from like 900 watts to 1500 watts to 2400 watts. Some of those servers might have 4 to 6 of those GPUs. You might be able to only accommodate a single server per rack, depending upon what the draw is and what that rack was originally designed for, right? So, and then from a cost perspective, that's a lot of wasted real estate. So, and what it really comes down to is a lot of the typical techniques and traditional techniques don't necessarily scale like they used to, right? Like a lot of the common threads of discussion when we talk about, processor performance, a lot of it's focused on like single-threaded, single-core performance, right? Which that's not a really accurate metric for how we determine, efficiency and computing power. Because at the end of the day, single-threaded performance isn't a realistic use case because we run multi-threaded applications. We take those cores and we divvy them up amongst multiple tenants in some cases. So using more efficient techniques will help us become more scalable in terms of how we do this. So even looking at legacy x86, the problems associated with hyperthreading, not just security issues, right? From a cloud provider perspective, if we look at just the difference between an Ampere processor, which has a single thread per core, versus x86, which has, if we use hyperthreading, the performance of that thread are going to be extremely jittery and not very predictable because the frequency of a hyperthread is that contention, right? Whereas when you move to a single thread per core model, we can deliver consistent performance to the application all the way through its life cycle. So from someone who's building shared infrastructure, it means that you can deliver the performance to the end user or your customer that they actually require in a very sustainable, predictable way and achieve, defined metrics of quality. Right? So, as we continue, right, like just thinking about it, we started out with virtualization hypervisors. When I started building what I would say the first iterations of what I would call a private cloud, and granted, I will say all my hypervisor experience is, VMware was GSX, for those of you who are old enough to remember that. That's my only VMware experience. Everything else has been Xen, KVM, or Hyper-V through its inception till today, right? So in the early days of building Linux virtualization clusters, a lot of it was taking from the application level clustering, right? Very complex, building these complex operating system management stacks on top of the operating system before we even get to instantiating the hypervisor, right? Just to glue those nodes together, right? Like very fragile, very difficult to maintain, difficult to set up. Once it ran, you kind of didn't touch it, right? And then, as the hardware evolved and we came out of pure power virtualization with Xen, we got hardware-aware virtualization. The virtualization movement kind of took off. VMware, obviously, as most folks know in the room, gained, a good domination of the market. And then through that, I think the evolution of other hypervisors being used to build standalone, other alternatives for management, including, OpenStack, CloudStack, OpenNebula, came into fruition. Now, we're thinking about it. We're 10 years past almost those original sort of development of those original cloud management or virtualization management technologies, right? And evolving into even more complex use cases and methods for deploying and those sort of things. Specifically like containerization and those technologies help advance the way we package and deliver software, right? Like, some people think that the lines of containerization and virtualization are blurred, but at the end of the day, a container is just a fancy software package that has the application and all its dependencies, including the operating system, which you can think of in this case just as a library, right? So it's the lines between virtualization and containerization are blurred, and now as we move even forward with micro hypervisors like Firecracker VM and those sort of things, the needs and the challenges of managing and all that are evolving, and the way we use it is evolving. So it's all as I like to say, it's my favorite space, right? Like private clouds are one of I guess my favorite technologies, because you get to glue all these different services together to provide an end service to the customer that, in my case, as a traditional IT guy, I didn't have to care what they were running, right? We're just providing the running water, so to speak, for them to feed their application. So, if we look at today, right, like given the momentum in the industry, specifically in the virtualization management space, with VMware acquisition, it's looking like there's a great opportunity for rebirth into, private cloud and a way to generate momentum into the next generation of that, on-prem virtualization infrastructure. So, if we look at this momentum of moving from public back into private or cloud repatriation, the numbers, there were some numbers that I said that I read recently where the level of cloud growth and the level of repatriation, they grow at roughly about the same rate. So when you sit there, it's okay, people are moving to the cloud faster. And once they get there, they realize in some cases it's more cost efficient for them to actually do it on-prem. So then they'll come back and they'll pull it back in-house, right? So there is a momentum behind that. One of the major reasons is it's difficult, right? It's difficult to take your interior infrastructure. It's not necessarily a lift and shift. In some cases, most people try to do that when moving to the cloud, but it's usually more expensive and complex than they expect. And typically, those who attempt to use a cloud is, for simple workloads, it's really not cost efficient to do that. You need to optimize those workloads to get the real balance of effectiveness out of that infrastructure. So, and as we said earlier, I've worked in OpenStack for a long time. Since Kubernetes came out, everybody was like, yeah, private cloud's dead. And then now we look at, they're reinventing private cloud with things like KubeVirt on top of Kubernetes, or deploying, the cloud's infrastructure as containers on top of Kubernetes. So it's just evolving, right? Private cloud's not dead, it's just changing. And, as I was saying earlier, as cloud consumption grows, so does cloud repatriation. So private cloud's not going to go away anytime soon. As we see here in Europe, the momentum behind greenfield new deployments is growing due to the nature of the business landscape. So what does it really all mean, for those of us who are building data centers and infrastructure and private clouds, right? It means the next frontier of computing is really efficiency, right? We need both data center efficiency, right? Because we have to reclaim that space. How do we make effective usage of all that money we put into that room, right? It's computing efficiency, right? We need to get the maximum density of compute into that space to ensure that we're doing it cost effectively. And obviously the software itself has to be efficient, right? Optimized, efficient, and both from its delivery standpoint and its run rate standpoint. So let's talk about like rack efficiency, right? So, if we look at real world web services, it's kind of comes down to, how many servers and racks do you need to deploy your infrastructure? And what does that really look like depending upon the infrastructure choices that you made, right? It could be, in some cases exponential difference, in terms of the real estate required. In some cases, if once again, that could be abstracted via cloud, but in all cases, it really comes down to what's the the size and scope of the computing infrastructure needed to deploy the services that I'm going to run on. And then, when we talk about, processor efficiency, right? And we look at, I guess the past a little bit. At Ampere, one thing we've always been incredibly focused on is, uh, processor efficiency. We have to compete in the same space. The way we look at it, though, like I said, is a little bit different. Traditionally, it's with Intel and AMD, we'd be focused on single thread performance on the core. And that's, with your spec JBP, your spec in, those types of benchmarks. But, that's not really that useful when we have to fit lots of compute in a small space. So actually thinking about it from the rack level performance or socket level performance, a little more realistic in terms of those types of workloads. So, and then, once again, component efficiency. So having an efficient general purpose processor, and the direction that the industry is going is more towards domain specific coprocessors or, daughter boards in that to help accelerate the specific workload. So, what I would say is there's a trend towards more tailored platforms to suit the workload application that's going to be run on them, right? Yeah, picking the right combination of general purpose CPU plus your domain-specific processors can hopefully lead to you building a more efficient and sustainable infrastructure. And then obviously, what we were talking about as well is the efficiency of the code itself. Containers and APIs made it easy to deploy. The orchestration and elasticity made it easy to scale, repeat. And then, modern DevOps techniques have allowed us to kind of maintain that in full CI/CD workflows in a much more automated, reproducible, and efficient environment. So, once again, going back to just applications in general, we started out with monolithic design, didn't scale, was less portable, less efficient, less elastic, single-threaded. We moved to distributed, multi-threaded processes, with microservice-based design that scales easily across cores, stateless, elastic, and efficient. And then, really, what does it mean? Well, it means the future of your compute is really about having processors that are designed for the current need of computing, right? Like if you continue to use what I would like to call legacy compute, you're inheriting the technical debt of their entire manufacturing process every time you buy that chip, right? In the case of Intel, you can see it on the board. So with us, with Ampere, we set out from day one to specifically design our chips for those workloads in the cloud, for hyperscale cloud. And what we actually did was we built a great general purpose CPU process, right? That just happens to be extremely energy efficient, right? So, really Ampere is the first modern semiconductor company. And we're building, the first cloud native processors to help try to achieve a sustainable cloud. So, and when we talk about that, we have two processor lines that are currently in the market, and we do that by really throwing a lot of cores at it. So we have the Ampere Ultra family, which the flagship chips in that, the Ultra, which tops out at 80 cores. Has it's like you can think of it as competing directly head to head with Xeon. So has all those server level features, L2, L3 caches, those types of things, single thread per core. Lots of high memory, pick up to 4 terabytes of RAM in the Ultra family. Ultra Max is built more for higher density, so you remove some of that L2, L3 caches to create more space on the die to jam more cores at it, right? All ARM-based Neoverse 8.2 compliant cores, and it's system ready, ARM system ready compliant, which for those who you are uninitiated of what that means, ARM has done a lot of work to standardize and certify, their SoCs to ensure that they have a first-person user experience similar to any other server on the market, right? So as long as it's ARM system ready, you can expect that you can take it, plug it in, and it's just going to be like every other server that you bought from that type of boot experience, management experience, how you install software. So, today we are the leaders in rack efficiency when you have, we can get in some cases, we have ODMs that are building 2U chassis that have over 1,000 cores in that 2U space, right? So because we use half the electricity of an Intel, we generate a lot less heat. So we can reclaim a lot of that data center space that you're wasting. Now, granted, if you're going to take those Ampere servers and populate them with GPUs, you're still going to have, like I said, 900 to 2,500 watts of electricity needed for the GPUs, but you can save roughly half of your electrical cost of what was budgeted for your processors because traditional Intel Xeon uses about 500 watts of electricity per socket. So that in a typical environment where you would have those GPUs, you'd probably use a 2-socket system. So you're talking 1,000 watts just for your general purpose compute. We can shave that to 500 watts and exponentially grow the amount of cores at the same time, right? Because of our high core counts. So you can save money, save power, and do more with less and less space. So, once again, like I said, we design with cloud native principles in mind. So that's, sustainable, predictable, scalable, and cost effective. Less power is the new power, right? So efficiency is where it's at. So, as I said, data center efficiency is the Ampere unique value proposition. So, more compute, less space, efficient compute, tailored for the needs of the cloud native. So, significant power and space reduction, right, is the real takeaway. And once again, because single thread per core with a pin frequency, you can have basically an SLA on the level of performance you can deliver to the tenants in your cloud. So, just a couple case studies, 8x8, they use it. They've achieved, 30% better price per performance in terms of using Intel when they switched. Kind of going into just leading into this, showing that there's other folks who have done it. Amadeus is another one. They got, better throughput, better performance, also at a better cost by switching. It's really just simple math. At the end of the day, you save electricity, save on cooling costs, price of the chip costs less, and you still get the high level of compute performance you would expect, right? And it's all coming back to how we architect the chips and that they're designed to have the highest performance server processors for cloud service providers and cloud deployments. So kind of our mantras, predictable performance, linear core performance, and the sweet spot of price, performance, and power. And then, Memento, another cloud-based company that we use as has been a user of our stuff. They saw 31 better performance by switching their VM instance type to an ARM-based instance. So we'll skip back. So yeah, once again, what types of workloads? One of the things we also focus on is inference, basically accelerating AI inference. So AI is all the buzz right now. So basically we're trying to prove that you don't necessarily need GPUs to do instance. In fact, when I was at Open Compute in November, Intel, AMD, and NVIDIA all came out talking about how AI is the future, how we need to do more to make it sustainable, how the things that they're looking at is liquid cooling because everybody wants to hire a plumber in their data center. And the reality of it is NVIDIA even came out and said you only get 65% efficiency if you're doing inference on your GPUs. And at $40,000 a pop for some of those high-end GPUs, why would you be wasting that workload? You should be using it for the things that actually you can get 100 or 98% utilization out of it, right? So. And then, just to close up, so as part of our AI initiative, we formed the OpenAI Alliance or Platform Alliance, and it's basically a lot of as we were talking about earlier, those accelerator vendors, non-NVIDIA based technologies, trying to do, break up that monopoly in the AI ecosystem space. And then for anybody who wants more information about Ampere, please come join our developer forums. We have some of the industry leading experts from the open source ecosystem. who've been able to, join and come and talk about, challenges of running on ARM-based servers. And then, you can come get updates in our newsletter, and definitely come check out our dev center. We can get more information about other people and companies using Ampere products to build their critical infrastructure and compute. Thanks, everybody. Appreciate you having me here today, and I'll the rest of the folks.